All right, so let's jump right in. We're all constantly making these invisible bets on the future, right? And we do it based on what we've seen in the past. Well, that logical leap, that's called induction. And it's this hidden engine that drives pretty much everything, from huge scientific discoveries all the way down to your daily decisions.
I mean, think about it. Ever seen dark clouds rolling in and just known you should grab an umbrella? Or maybe your favorite team has won every single home game, so you just know they're going to win the next one. If you've done that, you've used induction. That little mental jump from here's what I've seen to here's what's probably going to happen, that's exactly what we're digging into today.
Okay, so a really great way to think about this is to call it bottom-up logic. Seriously, picture a detective showing up to a crime scene. They don't just walk in with a theory of who did it, right? No way. They start at the bottom, with the clues, every single specific, individual piece of evidence, and they build their case from the ground up.
So here's the more, textbook definition. Induction is really the engine of empirical science. What does that mean? It means it's the process where you take a whole bunch of specific facts and observations, pile them all up, and then use them to build a general theory. It's how we make that crucial jump from, hey, I've seen this happen a bunch of times, to, okay, I think this is how things actually work.
Now, you can't really talk about induction without talking about its counterpart, deduction. They're like two sides of the same coin. So induction, as we said, goes from specific little details up to a big general idea. Deduction does the exact opposite. It starts with a big general rule and applies it down to a specific case. That's why we call induction the logic of discovery. You're finding something new. Deduction, that's the logic of confirmation. You're just checking if the rule applies.
Okay, so that's the theory behind it all. But to really get a feel for how powerful induction is, let's see it in action. We're going to watch it build a case, step by step, in the world of legal reasoning.
So let's imagine for a second. You're a lawyer, and you're trying to prove that this huge company has a serious, company-wide problem with how they write their contracts. Now, you can't just walk in and say, hey, there's a problem. You have to actually prove it. So how would you do it? How would you use induction to build your case?
Well, you'd start with the clues, just like our detective. Step 1, you gather up dozens and dozens of specific contracts from that one company. Then, step 2, you start noticing a pattern. Whoa, a really crucial detail is missing from every single one. And from there, you make the inductive leap. Step 3, you form your conclusion. The entire contract drafting process at this company is probably flawed. See? You've built this massive, powerful theory just from those individual pieces of evidence.
But, and this is maybe the single most important thing to understand about induction, that legal case shows us a critical truth. The conclusion you reach is powerful, for sure, but it's only probable. It is not 100% certain. I mean, think about it. Could there be one single, perfectly written contract hiding somewhere in a file cabinet? Yeah, maybe. So induction gives us really strong likelihoods, but it doesn't give us absolute ironclad proof.
And this way of thinking, it's not new at all. In fact, when you look at the history of induction, it's pretty wild. It shows us how our whole idea of what proof even means has changed over time. So the basic idea, believe it or not, goes all the way back to the ancient Greek philosopher Epicurus. Pretty cool, right? Then, much later, it became the super important tool in classical geometry. And from there, it just exploded, becoming the fundamental logic of discovery for pretty much all of modern science.
You know, early mathematicians had this great Latin phrase for it, reasoning in concreto. And all that means is reasoning through concrete, specific examples. So, instead of starting with a bunch of abstract rules, they'd start with an actual drawing, something tangible they could see and touch and work with. And for these early geometers, that was enough. If they could prove a theorem on just one perfect drawing, they felt it was just self-evident that the rule would apply to all similar shapes. That visual leap, this idea of seeing one thing to understand all things like it, that was considered a totally valid and powerful form of proof back then. So let's do a quick recap of what we've covered. First, induction is the engine of science. It's how we move from specific facts to create these big, general theories. But, and this is so crucial, it builds conclusions that are probable, not certain. And finally, as we just saw, our whole idea of what proof is has actually evolved a lot over time, thanks to this way of thinking. And all of this leaves us with one last, kind of mind-bending question to think about. If science, our greatest tool for understanding the entire universe, is built on induction, and induction can only ever give us probabilities, not absolute certainties, then what does that really say about what we call scientific truth? And what are the real limits of what we can ever truly know?